All right, everyone, if you could take your seats. I'm here to introduce Paul Ganssle, who will be speaking with you today about working with time zones and everything you wish you didn't need to know.
All right, they saved the best for last. But I think all those other sessions are closed, so you will have to stay in this one. Okay, so as Chris said, I'm Paul Ganssle. I maintain Datetime, and today I'm going to talk to you about working with time zones. So we'll start easy. We'll talk about UTC. UTC is the reference time zone. It is monotonic-ish. Why they decided to put leap seconds in the reference time zone and in civil time in general, I do not know. I sort of wish they had asked me. I would have said no. I think it's also important for you to understand the difference between time zones and offsets. So UTC plus 1 is an offset. That's the offset that applies now in London. Europe-London is a time zone. Time zone is a set of rules for what time zone offset and other time zone information applies as a function of the time. BST, which is the abbreviation that applies right now in London, is a highly context-dependent abbreviation. So in the context of London, it means British summertime, and that's UTC plus 1. But if you're in Bangladesh, that means Bangladesh Standard Time, which is UTC plus 6. And if you're in Papua New Guinea, it's Bougainville Standard Time, which is UTC plus 11. All right, so now this is the part of the talk that I'm sure is the main reason you came. I'm going to talk about all the weird stuff that people get up to with their time zones. You may have a friend, it's okay. I know you're asking for a friend, who thinks that there's only like 24 time zone offsets and they're all just exactly 1 hour increments away from UTC. But if you go to Australia, there are places that are half an hour away, or in Southeast Asia, you'll see some places that are multiple of 15 minutes away. And historically, it wasn't even true that that time zones had to be an integer number of minutes away. In Liberia, before 1979, they were 44 minutes and 30 seconds ahead of UTC. There's also the situation where you may think, well, the only time that offsets will change is if daylight saving time has changed, and vice versa. Daylight saving time will not change without the offset changing. But in 1992, Portugal decided that they didn't want to be on Western European time anymore. Instead, they wanted to be on Central European time. So they were going to shift their base offset by 1 hour. And they decided to do this at a time that would be convenient for humans, but it turns out to be kind of annoying for computers, which is when daylight saving time was going to end, instead of going from Western Standard Time to Western European Summertime to Western European Time, they just switched over to Central European Time. So the only thing that changed about the offset is that they went from daylight saving time to standard. So you can have a daylight saving time status change without any change in the total offset. As an aside, in 1996, they decided that sunsets, having the sunset after midnight was not a good idea, and they did the reverse. So after going from Central European time, instead of going to, I guess, Central European summertime, they just went directly to Western European summertime with no change in the offset. Okay, so now we know that a couple things that can happen. But you think, okay, well, if the only times that things will change is if the base offset changes or daylight saving time. And daylight saving time is obviously only once a year, right? Not the case in Morocco. So in Morocco, since 2012, there have been 2 daylight saving time transitions every year. So what happens here is, in the spring, they go on to daylight saving time. And then in this case, in 2012, they had, at the end of July, they decided to just turn off daylight saving time, and they'll just go back on to standard time. And then like 1 month later, they turn it back on. And people who've seen me talk about this before may know the spoiler that Morocco is a majority Muslim country, and this month is the month of Ramadan. And during Ramadan, Muslims are not supposed to eat until the sun goes down, so they would much prefer to be on standard time during that time. So they just said, well, let's just go back to standard time just for that 1 month. And they've continued to do that with surprisingly little notice every year. All right, so you say, okay, well, I know that there can be more than one daylight saving time offset change per year, but these only happen at like 2 in the morning, so I'm never going to see an ambiguous time or something like that during the day. But in 1994, Christmas Island, which I guess is part of Kiribati, they decided that they wanted to be on the other side of the international date line. This is some island in the South Pacific, and presumably they decided that one trading partner was more important than another one. I don't really know the details, but the upshot of it was that they decided they're not going to have a December 31st in 1994. It'll just go December 30th, 11:59, and then 1 minute later, Happy New Year. And you say, oh, well, that's just something that happens in the far past. This was the 90s. We were inventing programming languages and watching Seinfeld. You know, like, that's not going to happen today, right? But just 8 years ago, the same thing happened in Samoa. And historically, you've also seen things happen going the other way. So Kwajalein Atoll switched from one side to the other. And there were just 2 September 30th in 1969 in Kwajalein Atoll. You say, okay, fine. Daylight saving time changes can happen whenever, and there can be millions of them, and it's just chaos. But there's one thing that I can rely on, and that's if I know someone's location, I know what time zone they're in. But I think you know where this is going. In China, they decided that it would be a great idea to have one time zone for the entire country. And this is a country that normally would span 3 or 4 time zones. But I guess administratively it's easier. So they went with UTC +8, which I think is great in Beijing, like somewhere over here. In Xinjiang, which is far to the, now I have to remember east and west, the west of China, the sun rises about 4:30 in the morning, so that's not great. So they decided we're going to be UTC +6. But Beijing, the government does not like this. So all the trains and the post offices and all those things, they still run on UTC +8, and then the people just use UTC +6. And according to Wikipedia, the main difference of when you would choose which time zone is actually whether you are part of the Han majority or the Uyghur minority. So what this means is that this is actually a racial time zone. So I guess it is true that if you know someone's location and their ethnicity, then I suppose you can know their time zone. Okay, so I've scared you. I said time zones are crazy. There's no possible rules. Why would we want to work with these at all? Why not just like convert everything to UTC right away and never work with time zones? But time zones are actually very convenient. So if you're working with something like business markets or something, and they have a business close time of 5 o'clock during the weekdays, it's very easy for me to express this in an R rule and say every day at 5 o'clock, that's the market close, and it happens in New York, so I'm going to attach this New York City time zone. And if you look, if I print each of these, I always get 5 o'clock, and I have the right UTC offset applied for each one of these. And I can get UTC from this, so I can compare between time zones by just converting over to UTC. And if you look at it, it's not obvious how you would do this if you were just working in UTC, because then I would have to know when this 10 o'clock to 11 o'clock transition happens. And in fact, knowing that when those transitions happen is basically a time zone. So, so now hopefully this is the most convincing argument that you've ever seen that time zones are worth using. And we can just jump right into how Python represents time zones. Python uses tzinfo, which is an abstract base class. A concrete implementation of a time zone would be a subclass of tzinfo, and it's supposed to implement these 3 methods: tzname, UTC offset, and DST. As an aside, I would not recommend using this DST function. Anytime I've ever seen someone try and use it, they were kind of making some assumptions about daylight saving time that don't always apply. So I would just kind of stick to the tzname and UTC offset. But one thing that you should note is that each of these is implemented as a function of the datetime. So what these do is they get attached to a datetime, and then you call corresponding methods on the datetime, and it will give you this information as a function of the datetime. And I'm going to make this concrete by showing you this example implementation of a time zone representing Eastern time. And I don't recommend that you implement this, and you'll see why in a second. But what I've done is I have this isDaylight method, and I've implemented the other three as a function of that. It just says, if it's daylight saving time, if daylight saving time applies at this time, return this, or if it doesn't, return this other thing. And so if I construct one of these Eastern time objects, and I attach it to something on the daylight saving time side, I get UTC -4. And if I attach the same object to something on the standard time side, I get UTC -5. But what happens if I attach it to something that's in the middle, right? So if I go with the Eastern Daylight Time side first, right, I go to the last possible time before it switches, right, or close to the last possible time. If I say 1:30 Eastern Daylight Time, it looks like that works fine. 1 hour after that, because we're about to set the clocks back, should be 1:30 Eastern Standard Time. But in my implementation, if I do this, I get 2:30 Eastern Standard Time. Why is this happening? It's because I didn't properly handle ambiguous times. Ambiguous times are times like the one I just showed, where when you set your clock back, you're going to see the same time appear more than once. But as I mentioned earlier, the offsets are a function of the naive portion of the daytime, whereas these daytimes, 1:30 Eastern Daylight Time and 1:30 Eastern Standard Time, they're differentiated only by the output of that function, right? Which is the offset. So how do we handle this? Well, the answer prior to Python 3.6 is we don't. Throw your hands up. It's not possible. And you were just supposed to always return Eastern Standard Time. But in Python 3.6, PEP 495 fixed this by introducing the fold attribute of the daytime. And what this does is it adds a fold attribute, and that makes which side of that transition you're on a property of the daytime. So now you can write functions that take the local portion of the daytime and whether or not it's on one side or the other, and you return different tzinfo information based on that. And how it works is that fold defaults to 0, and if it's 0, it represents the first instance, and if it's 1, it represents the second instance. So now we can implement functions that handle the fold. There were other changes that went in along with this that have to do with comparisons of time zone aware datetimes. And so I'm going to just go into how the semantics of comparison work in daytime, because it's actually a little bit complicated. So there's two different regimes that apply. One is when the two daytimes you're comparing are in the same time zone. If they're in the same time zone, then the assumption is you only care about the local time. So in an ambiguous daytime, you'll see in most cases, this makes no difference whether you're comparing the absolute time or the local time, but in ambiguous times, the question is whether you care about the time the thing you want to be equal is the time that's shown on the wall, or whether it's like the time that it would be if you convert it to UTC. And they chose the time on the wall. So here you can see that if something is different only because of its fold, then those two things will compare equal. In the case of different zones, then they will just be converted to UTC and compared. So that's maybe more what you would expect, except when either datetime is ambiguous, in which case it just is like, whatever, it's false. I don't know. And I don't actually know why this is. It has something to do with hash invariance, and I'm sure that it has a very good reason, because the people involved thought about this a lot. All right, so I'm going to show you an interesting case that came up on the dateutil issue tracker for TZ. So here what I have is I've created a daytime that represents 1 a.m. on March 25th, 2007 in London. I convert it to a timestamp, and then I convert it back and get an object that represents, to the timestamp and then back using the London time zone, the original object, and then I create a brand new object that also represents London. It's the exact same data as there. And if I check whether x and y are equal to each other, I get false. So that's not a great start. But now x and z, those do equal each other, so that's good, but surprising that it's different. But at least that just means like y is this weirdo, but oh wait, y and z, so now we have this weird non-transitive relationship. And to explain why this is, I have to explain imaginary times. So an imaginary time is a wall time that doesn't exist in a given zone. So this happens when you push your clocks forward by 1 hour. So it'll be 1:30, and then 1 hour after that is actually 3:30. So Python is fine with you constructing a daytime that says like 2:30 in New York, or apparently 1 a.m. on March 25th, 2007 in London. So this 1 a.m. date that someone passed actually doesn't exist, right? So if I represent the 1 hour before and after this in UTC, I get midnight and 2 a.m. in London. So this happened during a transition. But that still really doesn't explain why it's non-transitive. I guess you could be like undefined behavior or whatever, it can do whatever it wants. But there's actually a reason why it's non-transitive. And the reason is that imaginary datetimes can't make round trips. Because once you map to something that's in UTC, you have an absolute datetime, and that will always map to some time that existed. So we start with our imaginary datetime, we convert it to UTC, and then when we convert it back, we get a different datetime. And so if you look, y and z were both products of a round trip because they went to timestamp and back. But we attached actually different time zones to them. Even though they represent the exact same data, the way the same zone, different zone semantics get applied is whether the time zones are exactly the same object. So because we have different object equalities, the first one, x and y, are using same zone semantics, and x and z are using different zone semantics. So in x and y, they just check whether 1 a.m., they just check whether this 1 a.m. and midnight are the same, and they say false. And with y and z or x and z, they convert them both to UTC. Both of them will get to midnight UTC, and those are the same, so you'll get true. All right, so now we know all the edge cases. There's no more left. And we'll go into like the practical aspects of working with time zones. So if you're working with time zones with dateutil, and I know the maintainer is a great guy, I recommend using these time zones. You can just attach them regularly to the datetime, and it's a little surprising that I have to say that, but you just use the constructor, you pass it to tzinfo, and it will give you this, it'll have the correct time zone information. If you have a naive time, or say we wanted to take that first datetime and then sort of reinterpret it to be in a different zone, so that it's at 2 o'clock in San Francisco, but everyone in the meeting moved to New York all at the same time, and we still want it to be at 2 o'clock. So we're just going to switch the time zone on there to US Eastern. It'll retain if you use replace, it'll retain the 2 o'clock portion and just change the offset. If you want the same exact time, right? So for example, if that first daytime represents a meeting that's taking place in San Francisco and someone from New York is calling in, we want to know what time it is in New York. We use as time zone, and that will do the conversion for the same absolute time. So that gives us 5 o'clock. With PyTZ, you can still use as time zone, but if you use the constructor or replace, it fails in this horrible way where it says like LMT, which is local mean time, and the offset is -4 hours and 56 minutes. So why that happens is because PyTZ's time zone model is actually different than Python's time zone model. In PyTZ, they expect all tzinfos to be static offsets. They don't change as a function of the datetime. And which one gets applied is determined by the time zone itself. So instead of attaching things directly, you would use localize. You would call the localize method of the time zone, and it would attach some object to your datetime, and that'll work. And then if you do anything to it, you have to normalize it afterwards. So if you add like 6 months, you'll it'll still say that it's in daylight time, even though it should have transitioned by then. So you have to call normalize, and then it'll fix that. This was important back before the fold attribute existed, and now it is considerably less so. And what we're left with is something that is not a great interface. And I know a lot of people who see this slide and they're like, I have to go fix code that's broken in production today. And there's more detail on my blog post called PyTZ, the fastest foot gun in the West, that explains more about the history and how things work. Okay, so when you're working with ambiguous times, you may have a couple edge cases to handle. So if you use as time zone, Datetime and PyTZ will both do the same thing because it's taking an absolute time and converting to another absolute time. But you'll note that PyTZ does not set the fold because they don't use the fold or need the fold. If you want fold support in, say, Python 2.7, you can use Dateutil's backwards compatibility method tz.enfold. So in Python 3.6, this just works. It just attaches a fold. In Python 2.7, what it'll do is it'll create a subclass that has fold whenever you need to use the fold, and then everything will just work. So Dateutil's time zones all use enfold internally, and so Dateutil will just kind of work even for Python 2.7. If you need to detect ambiguous times, like for example, you want to ask the user whether they should be on the daylight saving time or the standard time side of the transition, you can use Dateutil's datetime ambiguous, and that returns true if something's ambiguous in a given zone. And you can use this to selectively attach the fold if you want. But you don't actually need to selectively attach the fold. If you just say fold equals 1 for everything, it will be ignored for anything that's not ambiguous. To work with, there's a corresponding method for handling imaginary times. It's called datetime exists, and that will return false if a datetime is imaginary. And it's not terribly uncommon for you to say, well, if I land on this datetime, just tell me what time it is. Tell me what time it exists that that corresponds to whatever time it would have been if the same amount of time had elapsed after the transition had happened. So you can use Dateutil's resolve imaginary for this, and if the gap is 1 hour, it'll shift your datetime by 1 hour. And if the gap is like 24 hours or 17 minutes or some other weird thing, it'll figure that out and do it correctly. Okay, so in Dateutil, you can use, it has a couple of different implementations. It has UTC and static time zones. Both of these are actually in Python 3. So after Python 3.2, you really don't need Dateutil's tz.utc object or their tz offset. Those are just available in datetime. And if you want access to the INA database, Dateutil provides a method, getTZ, which will try and find the information on the system, and it will, and if it fails to find that, it'll use its own internal database that it ships. And this has historical information, so if it works in a modern context, it'll just show you Eastern Daylight Time or Standard Time. If you go back to the 40s, it'll have stuff like Eastern War Time, which was permanent daylight saving time during World War II. And if you go back far enough, you get back to that crazy LMT, minus 4.93 seconds, if you miss PyTZ. Just in general, the best way to get a time zone from Dateutil is to use tz.getTZ. So if you pass it nothing, it gives you local time. If you pass it something that is if you pass it something that is sort of a representation of your local time zone, like LMT4, or LMT is one of the time zones abbreviations, it'll give you a local time. And if you pass it an INA zone, it'll give you this TZ file object. Okay, so I'm just going to wrap up with some time zone tips because everyone always wants like the silver bullet, like how do I work with time zones? You have 35 seconds. And unfortunately, like that does not exist. It really all depends on your context. I would say one very important difference is civil times versus timestamps. A civil time is like a wall time. It's the time on the wall, and a timestamp is an absolute time, like the time in UTC. And civil, just know which one you care about and which one you're going to use. So if you're using a civil time, that would be for something like in the future, like a meeting or some kind of thing. And the reason why you would want to store this as the actual civil portion of the time plus the time zone, is that that mapping changes. So instead of just saying the meeting is next week at 12, let's store it in UTC and just change it back when the user's going to see it, you really want to say it's at 12, because if you convert it to UTC and then say the president says daily saving time is canceled as of tomorrow, which happens a surprising amount, then all your you've just lost that information. You can't recover it. So it's best to keep your abstractions close to what you actually care about. And then finally, the way that these things are serialized, never rely on those 3-letter abbreviations. They're ambiguous. The keys, like America, New York, or whatever, those are just lookups in the time zone database. If you want to show them to a user, pass them through CLDR, which will localize them and say in the native language, and they will be something that a user can look at. All right, so thank you very much for coming to my talk, and thanks to PyCon for putting on a great conference.
All right, we have enough time to take probably 2 to 3 questions, but I'm guessing Paul would be happy to speak after if you're not one of those 2 to 3 people.
Yeah, I can talk for as long as you need.
So we have this practice of pinning our dependencies so things don't blow up when we least expect it, when we're going to be building our thing or building our system. And it sounds like we need to be reinstalling dateutil every 30 seconds so that the stuff stays up to date. Because like how does it stay up to date when like something can happen like today and we need to be able to adjust to it? I don't know. How does that work?
So by default, dateutil will not use its own. It ships a zone info information, but that's mainly used on like on either Windows or on certain cloud providers, anywhere where the TZ data is not installed into the system. By default, dateutil has a number of paths that it'll look for the time zone information on, and it will pull it from the system if it's available. And I am hoping to at some point pull that data out of dateutil and have it be a separate package so you don't have to upgrade both the data and the code if you're on like Windows or something where it doesn't know where to find that information. But yeah, for now you kind of have to keep it up to date or make sure that you have TZ data installed on the system.
I actually wanted to defend those leap seconds. I come from space sciences, and all those leap seconds mean big deals to me.
Thank you for a prompt for me to talk about leap seconds, because I have some thoughts.
I have a few bad experiments.
No, I think that, I mean, my understanding was that most astronomers use Julian time and TAI or something, right? Which is monotonic, right?
Well, but this is FPGA experiments for ionospheric disturbances, and so our data is like, very, has to be right on. So those leap seconds are calculated into the position, yeah.
Yeah, I mean, to me, my main problem with leap seconds is actually just that it's in civil time, because if you're in space science or if you're in navigation or any number of situations where you need this information, I think people should be calculating it, and there should be a reference time that has leap seconds in it. But the average person does not need this information, and it's easy to calculate it as an offset from TAI. TAI is another reference time that is monotonic, but and it's like 17 or 35 seconds behind UTC. Who knows? You can maybe tell that I'm not great with details, left and right, west, addition and subtraction.
All right. If you want to talk more about Daytimes with Paul, I'm sure he'll be around. Otherwise, if you want to head down to Hall A, there are community awards happening, being presented by AWA, followed by a keynote and closing remarks. Thanks, everyone.